Hi, my name is Ruben, and in this video, I'll be giving a brief presentation about work on Weakly-Supervised Video Moment Retrieval. The authors are me, Huijun Xu, Kate Zanko, and Brian Plummer. In this paper, we are addressing the problem of Weakly-Supervised Video Moment Retrieval. This task differs from the strongly supervised variant, where we do not have access to temporal annotations during training time. Weakly-supervised prior work often leverages visual and language attention mechanisms to understand the relationships between a video clip and the description. However, they usually lack contextual information between frames that can be useful to determine how well a segment relates to the query. In this work, we propose to exploit fine-grained frame-by-word interactions to jointly reason about the correspondences between all possible pairs of frames, which provides contextual cues that are absent in prior work. As mentioned before, a key concept that is central to our proposed approach is the idea of frame-by-word interactions. The underlying intuition in here is that frames which are relevant to a word should have higher similarity scores as opposed to the others. To begin, we embed each word in the description using word-to-vec embeddings and encode each frame or clip using a convolutional neural network and a fully connected layer. Positional encodings, denoted as PE in this figure, are added to inject information about the temporal positions. These are then used to compute the cosine similarity scores between all possible pairs of frames and words. Using these similarity scores, we compute the frame-specific sentence representations, which are the weighted sum of the word embeddings for each frame. Likewise, we also compute the word-specific video representations, which are the weighted sum of the clip or frame representations that are specific to a word, and concatenate them with the original word embedding to create the visual semantic representations. These visual semantic representations are then passed into a second main component of LoGAN, which is the word condition visual graph. Instead of simply modeling relational context between video frames using a recurrent network as done in prior work, our word condition visual graph seeks to model the relationships between all possible pairs of frames. This is based on our observation that a video frame can be related to other frames in many ways, given different contexts as described by the sentence. To determine the relevance of each video segment or frame to the description, we adopt the log-sum exponential pooling similarity metric. Finally, we optimize the model using the triplet loss, where the negative samples are narrations and clips from different videos. We evaluate our proposed approach on two datasets, the demo and charades STA. On both datasets, the evaluation metric is the required K accuracy, where an intersection over union value above a certain threshold is considered a success. To start off, the demo dataset has about 8,400 and 1,000 videos in the training and both validation and test set respectively. This dataset differs from other video datasets in the sense that its videos are split into 5-second segments. We compare the performance of LoGAN to weakly supervised prior work as well as current state-of-the-art strongly supervised approaches. Significantly, we observe large improvement on recoil 1 accuracies, even over the strongly supervised methods. The charades STA dataset contains about 12,000 and 3,700 training and testing videos respectively. Since we are working with untrimmed videos in this case, we use non-overlapping windows of 128 and 256 frames as candidate proposals. Once again, we not only compare LoGAN to prior weakly supervised methods, but also current state-of-the-art strongly supervised approaches. Consistent with our results on the demo, our proposed approach outperforms weakly supervised work by a significant margin, across almost all metrics. Notably, LoGAN also performs comparably to the strongly supervised approaches. We also conducted a series of Bayesian experiments to understand the contribution of each component of our model. Please refer to our paper for additional details. Here, we provide an example visualization where LoGAN correctly predicts the temporal window in the video that corresponds to the query. We observe that the top 3 salient frames with respect to each word generally distribute over the same subset of frames. This suggests that our proposed model is able to identify the most salient frames with respect to each word. And that's it. Thank you very much for viewing our presentation. Due to time constraint, we cannot include as many details as we would like, so please refer to our paper for additional details if you are interested.